All right, so in these notes, we're going to cover the last two ways to prove triangles congruent. So let's just kind of take a second and review what we've done. Instead of having to prove that all three angles and all three sides are congruent in one triangle and another, there's actually, somebody a long, long time ago was super smart, determined that you could actually use these shortcuts. That means you only needed certain pieces of the triangle in certain orders, but you didn't need to have everything. So one of the ways, the shortcuts that we can prove triangles congruent that we've talked about is side, side, side. That's where if you had all three sides the same, you can go ahead and then say that the whole entire triangle is congruent. So if you have all the sides, then you also have all the angles. And we kind of talked about that in the past. Also, we've talked about side, angle, side. That's where you have to have two sides and an included angle that is touching both of those sides. If you just have those three pieces in that order, then you can go ahead and say the triangles are congruent. And the other one we talked about was for the right triangle, which is hypotenuse, leg. So in a right triangle, if you have the hypotenuses and one pair of legs, then you can say the triangles are congruent. All right, so we're going to add to that angle, side, angle, which is ASA. So you have two angles, and the included side of one triangle are congruent to two angles in the included side of the second triangle. So here it shows us an example of angle, side, angle. So what you have is angle A is going to be congruent to angle D. Side AC is going to be congruent to side DF. And angle C to angle F. So if you have these pieces, you have an angle, a side, and an angle. Angle, side, angle. So you can see both triangles have the same pieces in the same order. Therefore, you can conclude that triangle ABC is congruent to triangle DEF. And remember again, in this congruency statement, this second one, the order has to match the vertices. So if we went around this way, remember you have to go name consecutively in a circle, then we have to go DEF. And the way we know those are congruent is by the angle, side, angle, congruence postulate. Now, this whole thing, it talks about like included. So remember, included means in between. So in a triangle, the side that's connecting the two vertices, so see this side here, it's connecting those two vertices of the congruent angles, is referred to as the included side. And we've already talked about the included angle. So the included side is the side that touches both of the angles. So included means that the side, again, is in between the two congruent angles. Alrighty, so that is angle, side, angle. Next is angle, angle, side. So here you go. You have a picture here of angle, angle, side, angle, angle, side. So when you have two consecutive angles and then a side that's only touching one of them, you can say the triangles are congruent. So angle, angle, side. Now this postulate, you can be written as angle, angle, side, and it doesn't matter if you want to, sometimes if you reverse it, side, angle, angle. If you were to write this on your paper, just know, like mathematically, when we write things, it's typically in alphabetical order. So just flip that around so it's in alphabetical order. But these, okay, these are the same thing. It's two angles and then a side, okay? Two angles and then a side. So angle A is congruent to angle D, angle C is congruent to angle F, and side BC is congruent to side EF. So therefore, if you have two angles and then a side, you can say the triangles are congruent. And this is by angle, angle, side. So let's look at these examples. Can the triangles be proven congruent with the information given in the diagram? If so, state the postulate or theorem you would like to use. So again, given. You have to be careful about given. Remember, given does not necessarily mean it's marked and you can see it marked. There are things hidden that you're responsible for. So things you're responsible for, no, things you need to mark are vertical angles, are your responsibility, and another thing that's your responsibility to mark is the reflexive property. So those are, I mean, there's more than that, but these are the main two that you're going to see when we're working these triangles. All right, so in A, I see right away that these triangles are sharing a vertex, so I know it's my job then to mark those vertical angles congruent. Now I'm going to look at the pieces that I have on this triangle. I have an angle, here's another angle marked congruent, and a third angle marked congruent. Angle, angle, angle. Well, AAA is not one of our postulator theorems we could use, so no, these triangles cannot be proven congruent. So AAA is not one. Another big one that is not one is this one. Okay, that one cannot be used either. So just so you know, forwards or backwards, it cannot be used. So think about it. You can't have any inappropriate words in class. You're never going to be writing inappropriate words on your paper. So that is not a method that we're going to use to prove triangles congruent. Okay? Next, let's do this one. B, the triangles, what's popping out at me right away are that the triangles are sharing a side. So I'm going to mark that congruent. Then I'm going to say, okay, I have an angle here, another angle marked congruent, and then a side. I have an angle, and a side. So yes, they can be marked congruent by angle, angle, side. What you want to make sure of is that the angles are consecutive, so basically right in a row touching, and that the side is just touching one of them, so angle, angle, side. In C, the triangles are sharing a vertex, so it's my responsibility, your responsibility, to mark the vertical angles. Then you can see you have an angle, a side, and then an angle. So yes, these are congruent by angle, side, angle. So again, you can kind of just look at the differences here. So you can see the two right next to each other. Here, this side is congruent, and let's mark this angle again. So you can see the difference here. This is angle, angle, side, and this is angle, side, angle. So here, if you're going to say angle, side, angle, do you see how the S is in the middle here? Well, that means the side must be in the middle too. So wherever this S is in your postulator theorem, the side must be in the same place on the triangle. So kind of get that in your mind that everything needs to be lined up. So angle, angle, side, angle, angle, side. This side is not in between. All right, in example 2, can triangle STW, all right, so this one, is that congruent to VWT, this one? So let's see. We have, right away, I see a right triangle. So right triangles, what we always want to try first, and it's not necessarily always, but we always want to try hypotenuse leg. Well, what we have is we don't have the hypotenuse, so here's the hypotenuses. We don't know anything about those. What else I see besides the right is I see this overlapping side. So see, these triangles again are overlapping, so this side is congruent to itself. We have two 60s here and we have two 90s here. So if you look at these in order, you have an angle, and then if you're starting here, you want to go to the next piece that's marked congruent in both triangles. So see, necessarily I don't want to go this way because there's nothing congruent. I want to go this way and say, all right, that's angle, angle, side. If I try the other one, angle, angle, side. So yes, angle, angle, side. This one, the triangles are sharing a side. So I'm going to mark that again, reflexive. I have an angle here, a side, and then an angle. An angle, a side, an angle. So yes, Again, pay attention to where that side is at. If it's in between your angles, then you need to use the postulator theorem that has that there. Now, a little bit of different proofs. Again, we're not going to spend a ton of time on these, but I just want you to be exposed to them. You have completed 2-column proofs. So a 2-column proof, it uses arrows to show, this should say a flow proof. So we've done 2-column proofs. Now we're going to look at a flow proof. All right, a flow proof uses arrows to show the flow of a logical argument. So each reason is written below the statement it justifies. So remember, in a 2-column proof, you had statements and reasons, and then you numbered them. Here, this is just more of like a flow chart. So it is given that angle A is congruent to angle D, angle C is congruent to angle F, and BC is congruent to EF. So remember, always check over at your picture and make sure it's marked. All right, so then you have here, you have 2 angles and a side, 2 angles and a side. So we have here angle, angle, side, angle, angle, side. So basically, by the angle, angle, side method, you can say that these triangles are congruent. Now, and what's missing here, this third angle. Remember we talked about the third angle theorem? If you already have 2 pairs of congruent angles, then kind of by default, this third set, this third pair, they're also congruent to one another. So we can also say that B is congruent to angle E. It's not necessarily needed in this case, but you can say that. And then if you know that these are congruent, you could also prove these triangles congruent by angle, side, angle. So sometimes there are 2 different ways to prove triangles congruent, and as long as you have the correct statements and reasons, then you have a logical argument. Now, this last part is basically we're going to use congruent triangles. So it's kind of going backwards. So what we've done previously is we've used shortcuts to say the triangles are congruent. So if we have a few pieces, then we can say the triangles are congruent. So now we're going to take that and reverse it. So basically kind of like the converse. So by definition, congruent triangles have congruent corresponding parts. Corresponding. So what I'm saying is that we had some pieces and we were saying triangles were congruent. So now if we say triangles are congruent, then we know that their corresponding parts or pieces are also congruent. So if you can prove that 2 triangles are congruent, you know that all of their corresponding parts must also be congruent. And of course, we got to have a big fancy, new idea term behind this. It's called CPCTC. So, corresponding parts of congruent triangles are congruent. So, CPCTC. So that's why you can use CPCTC and you don't have to write all of that out. So let me show you how that works. In example 4, explain how you can prove that angle A is congruent to angle C. Well, right away, these triangles are sharing a side, so I've got to mark that reflexive. Since BD is congruent to BD because of reflexive, you now can say that the triangle ABD is congruent to triangle CBD because you have side, side, side. So now what you've done, remember how important I always say this statement is. So now, once you know the triangles are congruent, you can then pick apart all of the pieces that correspond and say they're congruent to one another. So you can now say that A is congruent to C. You can also take all the other pieces. B is going to be congruent to B, and D over here is congruent to D. So once you know the triangles are congruent, you know all of the parts are congruent. Let's look at example 5. So we're going to write a proof to verify the statement. So we know that AB is congruent to BD. All right, that was given. Then we know AC is congruent to CD. All right, that was given, and it's already marked on the picture for us. Now, because of the reflexive property, what can we state as being true over here? Well, the reflexive property is where anything is congruent to itself. So BC is congruent to BC. So now the triangles are congruent because of the side-side-side congruence postulate. So, since the triangles are congruent, so once you have this, again, this is like it's everything. Once you have all of this, you can then conclude that each and every piece and part is congruent. So angle D is congruent to angle A because of CPCTC. That's how you use that CPCTC. It's most likely in a proof situation. Other than that, you're not really going to see it too much.